Hi, I'm Fadlu and I'm responsible for hull design.
Hi, my name is Dion. I'm responsible for computer vision and simulation.
Hi, I'm Markan. I'm responsible for branding and media. As a starter, let me tell you about a thought experiment called Ship of Theseus. The ship of Theseus departed from Athens to Crete and it was made of planks. But over time, modifications were made on the ship to the point that there is no part of the ship that originally departed from Athens is a part of the ship anymore. One thing that is amazing about the ship of Theseus is how modifiable the ship is. This is the concept of modularity that became our main strategy for RoboBot 2022. There are some new tests for this year's RoboBot like Water Blast Challenge and Skiball Game Challenge. So we need more flexibility to do quick design iteration. By having a modular design, the quick design iteration can be easily achieved. Modularity allows our ship to divide it into independent parts. This part could be created, modified, replaced, and exchanged independently with other modules or between different systems. Moreover, a modular design allows us to ship the ASV as a flight baggage by splitting the ASV into parts that fit the dimension requirement for baggage.
Hull is the most critical component of Nala Theseus, as it is what keeps the ASV afloat. This year's tasks mainly require the ASV to optimize its stability. For example, in the Water Blast Challenge, our ASV needs to maintain its position and orientation as the water hits the target until the container is full. Also, a stable hull gives a better sensor reading. Stability focuses on the center of gravity, center of buoyancy, metacenter, and how these points interact to create uprighting moment. A ship with good stability will have a larger righting moment when influenced by wave disturbance. Therefore, we designed the hull that can reduce wave disturbance and remain stable under high amplitude and long length waves. To achieve that, we designed hulls with a relatively larger breadth to overall length ratio than our previous design. We use ANSYS software to analyze resistance and ship's motion by setting the environmental condition and the speed of 1.03 meter per second. As a result, our ASV is more resistant to pitch and roll motion when the ship is maneuvering. To connect the left and the right hull of our catamaran ASV, we use a frame made of steel hollow. Using this frame, the deck and hull can be separated, allowing us to configure the deck or even change the hull. The ASV only has one camera mounted on the midship, so it's easier to find the seat at the show challenge by maintaining the camera to face the dock's placards and move sideways. Like how a person finds his seat on the show, he walks sideways to have his eyes look for his assigned seat number. To perform this motion, Nala Theseus uses 3 thrusters. 2 of them are azimuth thrusters placed on the stern, and 1 is a bow thrusters. With these 3 thrusters, 3 types of motion can be performed: pivoting, orientation lock motion, and path following. Pivoting is when the ASV changes its rotation without changing its position. Orientation lock motion is when the ASV changes its position without changing its orientation. This allows the ASV to move sideways, and path following is when the ASV follows waypoints. Using 3 thrusters not only tackle the find a seat at the show challenge, but also support challenges like Water Blast where the ASV can perform pivoting motion to aim, and other tasks that require ASV stability to maneuver like avoid the crouch and snake run.
For the Skiball Game Challenge, we designed a ball launcher system that looks like a catapult. Our ball launcher is powered with a DC motor with speed and positional encoder. Using an encoder and a PID controller, the launching velocity of the ball can be kept consistent despite changes in battery voltage. A motor-powered catapult can also be used for the water blaster. In our design, the water blaster hose is attached to the end effector of the catapult. Since the motor position is controllable, the end effector can become the vertical aim system for the water blaster. Our strategy for Audi Challenge relies heavily on computer vision. The camera is used to detect objects in the autonomy challenges, as well as random obstacle buoys that is spaced throughout the ASV operating area. The LiDAR mounted on the bow of the boat was used to give distance information of the objects detected in the camera frame. Some challenges, like Snack Run, have buoy that, when entering the challenge, is 100 feet away from the ASV. Due to this, after trying several models, now Theseus uses one of the YOLO V4 architecture variants, YOLO V4 Tiny 3L, for its object detection model. This model was chosen for its speed and accuracy for small object detection. As this model is relatively small, it can be run at 15 FPS and on our onboard computer Jetson TX2.
Modularity allows us to create and iterate our ideas quickly. Those that show promise can be iterated rapidly until they take sufficient shape to be developed. Like Einstein said, learn from yesterday, live for today, hope for tomorrow. The important thing is not to stop questioning. Baru Nasra ITS,
Abang Putih.
Semangat, Go!
Woo!